Hello everyone. In this presentation, we'll be studying about regulatory enzymes. Regulation can be done by non-covalent modification, that is by allosteric enzyme. Regulation can be done by covalent modification, that by phosphorylation and rynization. And later parts of presentation, we'll be also studying about isozymes and zymogens. Now, regulatory enzymes can be regulated by two ways. One is by allosteric control, the other one is by covalent modification. In allosteric control, you have your allosteric activator which binds to a regulatory site. Okay, can you see? This is a regulatory site. The activator is binding to your regulatory site, causing a conformational change in your active site. See? Now, to this, your substrate can bind. Okay, once your allosteric activator has bound to the enzyme becomes active. Now, to this active enzyme, your substrate can bind and the enzyme can act upon your substrate. The other type of regulation is by covalent modification. Here, the enzyme is being covalently modified. That is, you're adding some extra groups like phosphoryl group or udryl group. Here, you're adding a phosphoryl group. Okay, so enzyme has been covalently modified. So once your phosphate group has been added to your enzyme, the enzymes acts upon your substrate, converting your substrate into product. Okay. Now let's study in detail about allosteric enzyme. Now in allosteric enzyme, you have a regulatory site. To that regulatory site, a modulator binds non-covalently. Okay. Now the modulator can have two effects. It can have an inhibitory effect as well as stimulatory effect. When your modulator is binding to your regulatory site of the enzyme and it is inhibiting the activity of that enzyme, then it is called as inhibitory effect. When a modulator is binding to your regulatory site of your enzyme and stimulating the activity of the enzyme, then it is called a stimulatory effect. Now, when your substrate and modulator are same, then it is called as homotrophic interaction. When your modulator and substrate are two different molecules, then it is called as heterotrophic interaction. Can you see here ligand, instead of ligand, you can see that if your substrate and modulator are two different molecule, then it is an heterotrophic interaction. When your substrate and your modulator are same molecule, then it is an homotrophic interaction. Now, allosteric enzymes are usually oligomeric. That is, it consists of multiple subunits. Okay. Now, allosteric enzymes have two binding sites. One is your active site where your substrate binds, which is same for all enzymes, and also you have other site called as regulatory site or allosteric site where your modulator binds. Okay. So in your allosteric enzyme, you have two sites. One is your active site to which your substrate binds. The other site is called as regulatory site to which your modulator binds. So the modulators are of two types. Positive modulator, which is also called as activator, which is enhancing the enzyme activity. And second type of modulator is your negative modulator, which is also called as inhibitor, which is inhibiting your enzyme activity. So you can see this is an enzyme to which your inhibitor, or you can also call it as a negative modulator, is binding. So it is binding to an allosteric site, okay, causing a conformational change in the structure of the enzyme. Now your substrate cannot bind to your active site. So there is a conformational change in the structure of enzyme. Now your substrate cannot bind to your active site. So your inhibitor is inhibiting the enzyme activity. Okay, in second case, you have an activator, which is also called as a positive modulator. Now, this activator is binding to the regulatory site, or you can call allosteric site of the enzyme, causing a conformational change in the structure of the enzyme. Okay, there is a conformational change in the active site. Now, to this, the substrate can bind to the enzyme, leading to the activation of your enzyme. Okay. So binding of modulator is causing an conformational change in the allosteric enzyme, which is influencing their catalytic activity. Allosteric enzyme do not obey Michael-Menten's kinetics. Okay, when you draw a graph versus reaction velocity versus substrate concentration for a simple enzyme, you get an hyperbolic curve. But for an allosteric enzyme, when you draw a graph versus reaction velocity versus substrate concentration, you get a sigmoid curve. Okay, why do you get a sigmoid curve in case of allosteric enzyme? We all know that allosteric enzymes are oligomeric protein, that is, it has multiple subunits, okay, and these multiple subunits are acting in a cooperative interaction manner. Okay, because of this reason, you're getting a sigmoid curve in case of allosteric enzyme. Now let's learn about regulation by reversible covalent modification. Okay. Now here what is happening is that your enzyme is being activated by adding some groups. By covalently attaching some groups to the enzyme, leading to the activation of that enzyme. Like your enzyme, your phosphorylation, that is addition of phosphoryl group. Okay, leading to the activation of that enzyme. In the addition of adenyl group, that is adenylation, addition of uridine, that is uridylation, addition of ADP ribose, that is ADP ribosylation, addition of methyl group, that is methylation. So by phosphorylation, adenylation, uridylation, methylation, you are covalently modifying the enzyme and activating the enzyme. Now phosphorylation is the most common type of covalent modification. Now let's study about enzyme called glycogen phosphorylase. Okay. Now this glycogen phosphorylase is an enzyme which catalyzes the first step of gluconeogenesis. Now what is gluconeogenesis? Gluconeogenesis is nothing but the breakdown of your glycogen into to release glucose in the form of glucose 1-phosphate and glycogen from glycogen chain where one glucose has been removed in the form of glucose 1-phosphate. And this first reaction is being catalyzed by enzyme called glycogen phosphorylase. Okay. Now this what it is doing, this glycogen phosphorylase? The glycogen phosphorylase is breaking alpha 1,4 glycosidic bond from the non-reducing end. Okay, can you see this is alpha 1,4 glycosidic bond? That bond is being broken by this glycogen phosphorylase to release one glucose in the form of glucose 1-phosphate and a glycogen chain where one glucose has been removed. Okay, that you can see N-1. Now we'll be studying that this enzyme is being activated. It exists in two forms. One form when the phosphate group is added to this enzyme. When the phosphate group is added to the enzyme, it is active. And when the phosphate group is removed from the enzyme, this enzyme is inactive. Okay. Now let's see the steps of gluconeogenesis. This is a glycogen. Now glycogen is broken down into glucose 1-phosphate by enzyme glycogen phosphorylase. Now glucose 1-phosphate is being converted to glucose 6-phosphate by phosphoglucomutase, and glucose 6-phosphate goes to the muscles where it provides direct energy. And later if glucose 6-phosphate is being converted to glucose by glucose 6-phosphatase, it goes to the liver where it is stored in the form of glycogen. Okay. Now we are studying about enzyme called as glycogen phosphorylase. Okay. Now this glycogen phosphorylase exists in two forms, glycogen phosphorylase A and glycogen phosphorylase B. Now glycogen phosphorylase A is a phosphorylated form which is the active form of the enzyme which can convert your glycogen into glucose 1-phosphate and the chain, glycogen chain, where one glucose has been removed in the form of glucose 1-phosphate. Okay. Now the phosphorylation of this enzyme is being catalyzed by phosphorylase kinase, and removal of phosphate group from this enzyme is being catalyzed by phosphorylase phosphatase. Okay. So you know that glycogen phosphorylase exists in two forms. One is the phosphorylated form, which is the active form, and the non-phosphorylated form, which is the inactive form. So we know that glycogen phosphorylase, the first enzyme of gluconeogenesis, exists in two forms. One is a phosphorylated form, which is the active form, okay, and see this is the active form, and the non-phosphorylated form, which is the inactive form, okay. Now the phosphorylation of this enzyme is being catalyzed by kinase, and the dephosphorylation is being catalyzed by phosphatase, okay. Now, where is the phosphorylation taking place? It is specifically taking place in the serine residue of this enzyme. Okay, the serine residue of this enzyme is the place where your phosphorylate group is being added by phosphorylase kinase to activate the enzyme. Now let's see, there are from this table you can see there are few more enzymes which is being activated by phosphorylation and adenylation. Now in case of glycogen phosphorylase, addition of phosphate group is activating the enzyme. Okay. Now here in the case of glycogen synthase, Removal of phosphate group is activating the enzyme. Okay, so there can be cases where removal of phosphate group is also activating the enzyme. Okay, so addition of and here you can see addition of adenyl group is activating the enzyme. Addition of ADP ribose is also activating the nitrogenase enzyme. Okay, so what we saw that by covalently adding some group, you are activating some enzymes. Okay, by adding covalently phosphoryl group, adenyl group, uridine group, you are activating the enzyme. Okay, there are also enzymes where your removal of phosphate group is also activating the enzymes. So now let's understand what do you mean by isozymes. Now isozymes are the enzyme which is catalyzing the same reaction, but they differ in amino acid sequence and composition, substrate affinity, Vmax and other physical and chemical properties. Now let's here understand 5 isozymes of lactate dehydrogenase. Okay, so these are the 5 isozymes of lactate dehydrogenase, and all these 5 isozymes are catalyzing the same reaction, that is conversion of your pyruvate to lactate. Okay, and the H4 is one type of lactate dehydrogenase H, that is a lactate dehydrogenase 1. H3M is the second type of lactate dehydrogenase. H2M2 is the third type of lactate dehydrogenase. HM3 is the fourth type of lactate dehydrogenase. M4 is the fifth type of lactate dehydrogenase. Now each lactate dehydrogenase is a tetramer. Like H4 is the first type of lactate dehydrogenase which is made up of 4 H unit. H3M is the second type of lactate dehydrogenase which is made up of 3 H unit and 1 M unit. H2M2 is the third type of lactate dehydrogenase which is made out of 2 H unit and 2 M unit. Okay, and this is HM3 which is a fourth type of lactate dehydrogenase which is made up of 3 M unit and 1 H unit. And M4 is the fifth type of lactate dehydrogenase which is made up of 4 M units. Okay, so these are the 5 isozymes of your lactate dehydrogenase, and each of them are present in different tissues. Like that H4 or lactate dehydrogenase 1 is present in your heart muscles. H3M is present in your RBCs. H2M2 is present in your brain and kidney. M3H is present in your liver. M4 is present in your skeletal muscles. Okay, so all these isozymes of lactate dehydrogenase are catalyzing the same reaction, that is conversion of your pyruvate to lactate. But all these isozymes of lactate dehydrogenase have different physical and chemical properties. Like they have different Vmax value, they have different substrate affinity, they have different amino acid sequence and compositions. Okay, but all these isozymes are catalyzing the same reaction, that is conversion of your pyruvate to lactate. Now let's understand what you mean by zymogen. Zymogen is nothing but an inactive precursor of an enzyme is called a zymogen. Can you see this is a zymogenic form of this enzyme? Okay. Now a protease is removing this extra group from the zymogen and it converting it into an active enzyme. Okay. Now once how is it converting? Because this protease has removed this extra group, causing the active site to open. Now your active site of this enzyme is open and the enzyme has been converted to active form. Now majority of your proteolytic enzyme like chymotrypsin and trypsin are being synthesized in the form of zymogen. Okay, trypsin's zymogenic form is trypsinogen. Chymotrypsin's zymogenic form is chymotrypsinogen. Okay. So in duodenum, the pancreatic zymogens such as trypsinogen, chymotrypsinogen, proelastase, procarboxypeptidase are being converted to active enzyme by enteropeptidase and trypsin. Can you see this is trypsinogen, which is an zymogenic form of trypsin. Now trypsinogen is being converted to trypsin by enteropeptidase or enterokinase. Now trypsin is converting all these zymogens to their active form. Trypsin is converting chymotrypsinogen to chymotrypsin. Trypsin is converting proelastase to elastase. Trypsin is converting procarboxypeptidase A to carboxypeptidase A. It is also converting procarboxylase peptidase B to carboxypeptidase B. Pro-phospholipase A2 to phospholipase A2. Pro-colease to colease. So trypsin is also converting all this zymogenic form to their active enzyme. And enteropeptidase is converting the trypsinogen, the zymogenic form of your trypsin, to trypsin. Now there are a few questions here which you can solve easily if you have understood the presentation clearly. Thank you.